Okay, good morning. Good morning, everybody. It's great pleasure to have Professor Tae-Hwan Kim as a today's speaker at APCTP seminar. So we are organizing this online seminar almost every week. So please visit our website frequently. So you can check out interesting seminars organized by our center with many distinguished scholars. For example, in 2 weeks, we're going to have a lecture series which will be given by Professor Hae-Young Ki from Toronto University. So today's exciting talk is about unexpected two-dimensional chiral orders in one-dimensional charge density wave. Please welcome Professor Tae-Hwan Kim. Okay.
Thank you. Nice introduction. Hello, everyone. I'm Tae-Hwan Kim. So today I'm going to talk about maybe not familiar with you. So one keyword in the charge density wave, and the other keyword in the chiral order. So I will briefly introduce what is chirality. Maybe you know very well, but I'm just for the beginners. And then I move to my system. It's a coupled double Pier chain, which is actually indium nanowire grown on the silicon surface. Then finally, I will talk about today's main subject in the 2D chiral order in the one-dimensional charge density wave. Okay. So what can I do? Okay. So before going on, I would like to introduce my colleagues for this work. I have a very lucky work with a very nice theoretists. Actually, this two guy is mainly focused on the density function theory calculations, supporting our observation. And Professor Sang-Woo Chun is a very nice guy. Actually, his background in the particle physics, so he's very know well about in the symmetry of systems. So he is helped me a lot about analyzing the symmetry of the system and give some idea to influence. Okay, so let's start is a very basic one. It's a chirality. So we know that it's a chiral, right? Our hand is a very famous object, which is a chiral object. So this chiral actually comes from Greek word, which is hand. So it's our hand, left hand, right hand is not, looks similar, but it's not identical. So when you put in your left hand glove on the right hand, so you feel very uncomfortable, right? So this is not the same. But this chiral terminology is come from actually in the Lord Kelvin. Actually, he used in the first time in the scientific talk. So what is he said is actually he's defined chirality as it's a mirror image. It's not be brought to the original shape, which is cannot be brought means is using in the continuous operation like a translation or rotation. So mirror and immersion actually not continuous transformation. They are abrupt switching. So on the other hand, we can define this kind of chiral object using the broken symmetry, which is a broken mirror symmetry or broken inversion symmetry, then lead to definitely lead to in the chiral object. So right here, so this red rectangular represents the mirror. So if this is your left hand or right hand, then the mirror image becomes left hand. But these two cannot coincident just using translate and the rotations. Okay. So then is this chiral actually use many fields with the different and the meaning. But today I'm focused on the geometrically fact, so which is mirror symmetry of the structure cannot coincident with the original structures. So like here, so this geometric broken symmetry can lead to the chiral or the isomer in the biomolecule. So here, actually, fever refers medicine. Actually, when you synthesize this medicine, actually, always there has two molecules synthesized at the same time. But this one is active, the other is they don't have any effect. So with some side effect, which is stomach ache. But nowadays, there are company only select one chiral molecules that make it more effective in the medicine. And also, our DNA also chiral, which is helical double strand. Maybe due to that, but many in the living creature has chiral structures, like this in the climbing plant has a certain winding direction, and also sea snail has their winding as actually their predominant winding exists, but is their counterpart also rarely found in the nature. In the physics, we very well know about in the circular polarized light, their polarization keep rotating certain direction due to the chiral structure. Also, particle physics, we can define is a relationship between the momentum and spin. Then we can define the one is left-handed chiral, the other in the right-handed chiral. Also, recently we worked on it in the indium nanowire to find that there has a very interesting topological soliton, which we called is a chiral soliton. Well, we'll discuss it later briefly. Okay, this chirality actually we can easily found in the spin system. For example, here 1D magnetic ferromagnet, we have left-handed and magnetization. If connected in the right-hand magnetization on the same chain, then we have to rotate in the spin direction two ways, right? In the left-handed or right-handed, right? This is a nail magnetization or blow magnetization also. We have two choices. Because of this chiral actually come from in the vector nature of these order parameters. The spin itself always direction, so we have to rotating in the two ways. And also antiferromagnetic one-dimensional system also has these chiral structures. And the two-dimensional, we have very nice example, scomium, and the scomium, antiscomium, they have different and the spin textures, and we have in the distinguished topological invariant. And also biosemimeter has a three-dimensional the monopole, monopole and the anti-monopole. Actually, this is not a real spin system. This is live in the momentum space. And anyway, their structure is actually the same as we so-called in the monopole and anti-monopole. As you can see here, in the spin system, we have one-dimensional, two-dimensional, and three-dimensional and chiral structures. But what about, okay, this is the experimental observation, but I will skip. And but what about the charge order system, especially in the charge density wave cases? Actually, many people cannot hear about in the chiral charge density wave. That's I will explain the why they don't have a chirality, especially one-dimensional cases. So here, one-dimensional charge density wave. Actually, this model is polyacetylene. It's one of the famous conducting polymer. So this is actually ideal metal state. So it's all bonding is satisfied, but they have one extra electron live in each carbon atoms. Then this extra the remaining electrons and come together, lead to forming and additional bonds. So then we have double and single and double and single alternating structures. But this bonding ordering can be happen the other way. So we have two degenerate ground state. But these two ground state actually not the exactly same. Of course, energetically same, but they are topologically different. So here, the band structure of each phase. But it's this phase, if there has infinite wire, they have no difference, but they have a different edge structure. So due to that, actually, the topological feature actually different. Actually, this color is due to the eigenstate in the pseudospin vector. So if you plot the pseudospin vector near in the band gap, the one phase actually the back and forth within the pseudospin vectors in the blow sphere, but the other one in the fully rotate one turn. So this distinct difference actually give in the topologically different structures. So in these two one can meet together, then is this edge or boundary can be not normal, which is we call it in the soliton, topological soliton. So one phase and the other phase sit on each other. Then is their order parameter. Actually, one is positive, one is negative. So it's this negative part should be connected continuously. So the other way also same thing. Then is the edge actually topologically excited as in the topological soliton. So this actually, we have an analytic solution when you're solving this effective Dirac Hamiltonian. Then we have a hyperbolic tangential function can describe in this soliton. Actually, this y-axis is order parameter. Here, order parameter as displacement, atomic displacement. So here, equal distance, but is when you dimerize, then is they're positive, then becomes A phase. This is negative, it becomes B phase. Then this different order parameter can be connected with these two soliton and anti-soliton. But here we don't have any directions. We only have a magnitude. That's why we don't have any chiral structures. So let's compare more clearly with what's difference between the spin and a CDW system. A spin, when you have this, consider this two situation. So at first glance is they are similar, right? Actually, when you look carefully, this is spin rotated counterclockwise, and the keep counterclockwise, so they are chirality same. But here, they are rotating clockwise when you're moving along this chain direction. But here, back to in the counterclockwise. That is when you plot this angle change along the chain, then it start from 0, so from here, then rotate in the pi, and then rotate another pi, then becomes 2 pi. But in this case, start from 0 to pi and come back to 0. So these two difference actually told different response with respect in the external magnetic field. When you apply the magnetic field in this system, actually we cannot remove in this domain. When you apply the magnetic field in the up direction, but still they're winding, keep winding in the 2 pi winding cannot break. So we need a huge magnetic field to destroy this one. But in this case, when you apply the magnetic field in the downward, then it's a downward domain, it becomes bigger, but with the expanse in the upward domain. But finally, they're merging in the totally in the ground state without any this kind of a domain work. So these two is totally different. But in the here, this is the charge density wave case. They don't have this kind of things like here. They only have positive and negative. So always connected start positive to the negative, then this negative should be with like negative to positive, which means in the CW case is always in the solid tone, anti-solid tone pairs appear same time, disappear same time. But here they can survive in the same chirality, but different chirality they cancel out, so they can annihilation at the same time. All right? So one-dimensional case maybe don't have intrinsic chiral CW cases, but what about the two-dimensional? Actually, 10 years ago, so one group has reported they found the chiral order in the two-dimensional charge density wave, which is 1T titanium diselenide. So 1T diselenide atomic structure like here, then is they found when you cool down, they notice there is a 2 by 2, actually more complex because there has a 3 unit cell vector, right? So each unit cell vector is dimerized. So it's a 2 by 2 by 2 superlattice should be up here. Then they, if they don't have any color, then should be this fixture. So each color represented one direction's CWQ vector. So 3 equivalent CWQ vector exist in one plane. So they don't have any color along the even G direction like here. But they found using the STM and different location seems different CW pattern. So they analyze their fast Fourier transform image of each STM image region over here. They found some Q vector is highest intensity, the other against the other two, which means they are assigned in the chiral like here. Start from the highest, middle, and the lowest. So they found the two different chiral order. To explain this kind of unusual behavior, they propose one scenario, which is each layer, one of and the Q vector for the CW is dominant. Then, when you stack this layer, then they are rotating, like 102 degrees, as you can see here. So start with the red and the green, blue, and this order, this order. The other order is opposite order, red, blue, green. So they distinguish this is chiral. So they claim their first observation in the chiral order in the charge density wave system. But later there is some debate. Then finally, in the 2018, another group actually did more soft case analyze using in the interstitial titanium defect. Actually, this titanium defect can visualize more clearly underlying lattice distortions. So they analyzing very carefully, then they concluded each layer actually indeed there has some periodic lattice distortion, very small. But it's this periodic lattice distortion, nothing to do with in the chiral charge density state charge CDW order. So one example here, they crop in the top layer and the bottom layer, which is a different layer. So previous scenario, different layer has different CW structures. But in the here is a zoom in image in the bottom layer and the top layer. But as you can see here, they don't have any difference. So almost identical, which means that they don't have any phase difference between the different layer. So actually denied in the this scenario. And also they confirmed the the wanted titanium diselenide structure, even at the CDW, they still preserved in the inversion symmetry, which is they don't have in the any chiral structures at all. But surprisingly, later in the another group, very recently this year, they reported in the very nice example of this chiral properties, which is they use in the circular polarized light to measure their optical response. Basically, they are measured optical transport. So they make this kind of structures using the thin flake on top of matter. Then they shine the light, then measured in the photo current. So first they do in the just cooling. Here the people actually is a little bit lower than the room temperature. And anyway, in the high temperature, they measure the photo measurements. When you're changing circular polarized light, but they don't have any response. But when you cool down, then this is formed the CDW. If this CDW is a chiral, they should be response differently, because in the chiral structure, actually so-called optical activity, which means their absorption is different chiral circular polarized light. But here also they don't have any change in the photocurrent when you change polarity of in the circular polarized light. But they did this very nice approach, which is that they first shade the circular polarized light, left the circular polarized light on the sample, then start to cool at the low temperature. Then cut off this light, then start to measure the same thing over here. But as you can see here, different chirality of circular polarized light, they have a low photocurrent, but same chirality when you cool down, then they have a higher photocurrent systematically right here. Then they warming up, then basically reset, and then they change the polarity of circular polarized light. Now it's the right chiral, light circular polarized light. Then cool down, then we see in the different response. Then actually they finally confirmed the titanium diselenide has a chiral form when have in the circular polarized light. Otherwise, they don't have like here. But still, we don't know. Actually, the author also opened leaving in the open question, because they're using is broad in the laser to measure the photocurrent. So they don't have any idea about this micro mechanism to have a really chiral structure in this sample, or they have basically on chiral but induced the chirality later, applying it in this circular polarized light. But anyway, they have finally confirmed in the 2D CDW structure also becomes chiral when the condition is satisfied. Okay, so let me summarize very shortly. 2D CW, actually, they showed induced chiral CW order, but they don't still yet the intrinsic chiral CW. But one-dimensional, they don't have any the induced or the intrinsic chiral structures. But what about in the quasi one-dimensional CW cases, which is a coupled double Piers chain? Actually, there is two simple 1D chain, then interact with each other. Then they have is a so-called chiral solitons. This chiral meaning actually a little bit different, but is they have actually give some clue. Maybe this system also becomes chiral order in the intrinsically. So let me introduce. Yeah, sure.
So So the question is, you said in 2D CDW, you can induce, some other group demonstrate they can induce so-called induced chiral CDW.
Yeah.
But what you explained in previous slide is just the system become chiral, but they didn't check whether this chirality comes from CDW or is related to CDW.
Oh, that's a good question. Actually, that point also leave it in the open question because they confirmed in the CW transition way higher than this induced so-called actual gyrotropic effect. The gyrotropic effect is transition temperature much lower than in the simple CW's transition temperature. So they claimed in this gyrotropic effect and the CW can coexist at the same time. So maybe is CW itself not chiral, but it's electron structures actually becomes chiral when you under irradiation of in the subtopoloid light, but still needs some more investigation to answer this question.
So the fact is that when they have this chirality induced by external polarization, then system simultaneously have CDW state, but it's not clear whether this chirality and CDW is connected or not.
Yeah, it's still
okay.
Open question. Because they use it in the average, right? Ensemble average, but cannot tell. So there, the simple idea is when you cool down, actually there in the two different chirality exist in the exactly same population. So apparently a chiral, but when you in the circular parallel light cool down, then is making dominant one part. Yeah. Yeah. But it's cannot checked with experimentally. Yeah.
Then connected question is that at least theoretically, can you explain this optical chirality by one of the CDW picture you explain this 3-layer keep rotating?
Oh, they don't have any because that rotation actually does scenario not confirmed.
I know, but
yeah, but
suppose that scenario.
Actually, this can be ruled out because this is actually 3 different chiral structures at least. But here talk about is the winding actually one chiral.
Right.
The other winding is the other chiral.
Yes.
So there's only 2 chiral.
So but, here you also have only 2 chiral.
Yeah. Here also same thing actually. In that sense, actually, it can connect it. But
so my question is, suppose theoretically you have that kind of CDW state.
Mm-hmm.
From that state, can you explain this optical response?
Not easy actually.
Not easy.
Yeah.
Okay.
Yeah.
Thank you.
Yep. Okay, move on to actually this system is quite complex, so maybe they might need more time to explain the more kindly, but it's to the time limit I have minimized this explanation as possible as possible. Yeah. Okay. So in this one actually the grown in the silicon surface just one layer in the indium atom. So this blue ball actually represents each indium atom. So as you can see here, 2 zigzag chain actually formed this one wire. So this is a metallic phase. They have equal distance, but when you cool down, when you focus on the outer chain is become shorter distance, longer distance, shorter distance, longer distance, alternatively. Okay, that is dimerized effect. And also additional shear phonon making this whole structure as a so-called hexagon structures. But this is usually too complicated. I usually preferred using in the simpler one. Actually, this each zigzag chain we can represent by in the one simple atomic chain. And also this can be dimerized, like here, Pierce instability. Then is we have interacting double chain system. So the this formation is very well known in using the Defect calculations. So this final CW form is a hexagon, actually mixture with the two phonon structures. One for the shear mode, each layer moving in the along the chain opposite way, and the other is actually rotational rotary mode of phonon. But this rotary mode phonon actually involving the one chain. So the other chain also same rotary mode. So each rotary mode has two configuration. So the shear mode is two choice, left hand, right. And this also clockwise, left clockwise, in the different atoms. So in combination of 8, so we expect 8 ground state in here, but we only found is a 4 ground state in this system. Because here, so this upper rotary mode, lower rotary mode combined together, then we have a so-called trimodal. But this trimodal, we have 4. Each one has 2 choices. So then we can plot in this each ground, tentative ground state at the order parameter space. And the x-axis is the dimerization direction. So this is positive and this is negative. And the y-axis is represented interwire coupling direction. So this is positive and this is negative. So we have 4 choices. Then, given one trimodal, so there are 2 identical, then we have 2 choice of shear phonon mode. So one making this one, the other direction making this one. But as you can see here, this shape is different, and also their energy is so different. So this is a stable form. This is a way high formation energy, so it's not allowed. So in the overalls, we have only one choice with a given rotary mode, because 2 choice of a shear mode is one only can allowed in the stable ground state. So in that sense, and each in the rotary trimodal has 2 choice of and shear mode. Then we know that in the one of them is not allowed. So then we find that this is a foreground state, like here. So that is our basic starting point.
So you can have dimerization along the x direction.
Yeah.
So you have plus minus mass along mx.
Yeah.
Now you also introduce the mass along the g direction.
Yeah.
So in terms of original picture, that means dimerization along g direction.
Oh no, it's interwire coupling. So this blue atom actually interact with the unbonding the 2 atom in the upper chain, right?
Yes.
But this one is interact with the bonded 2 atom. So this difference actually presented in the mg in the y direction.
I see.
Yeah.
Okay.
Yeah. So then also we make you construct in this effective and massive Dirac Hamiltonian. Then when you solve it, we have 4 ground state. The energetically identical, so degenerate 4 ground state. So in the auto parameter state over here. So actually, like here, we defined in this way. Yeah. So indeed, we can find is 4 different ground state in the experimentally. So as you can see here, different in the CW configurations appear in the same sample. So and actually this is different wire, okay? Then as you can see, so they're moving different location due to the different structures. And also in the auto parameter space, we have 12 connection between any two ground state, which is this the arrow actually present as a soliton because the two different ground state connected to one chain. So it's they should be connected smoothly, which is excited in the topological soliton. We call it actually a chiral soliton. As you can see here, is a four of them is rotating in the clockwise in the autoparameter space. You get it red, orange. Okay. See the orange colors. Then we called in the right chiral soliton, and the other way in the left chiral. So moving through in the origin, actually they don't have any chiral direction, right? Then we call it a chiral soliton. So this is three represented atomic model of for the each right, left, and chiral solitons. And this soliton also we can find in the using the STM in the real space. So as you can see here, H1 is exactly the same at the previous atomic model. And also we can predict using the tight binding calculation, their SM profile can match well with the real profile. So as you can see, the two close to each other. So SM profile is the black, but tight binding calculation is blue. So as you can see, they are almost 100% perfectly is matched well. And also this is STM height profile, apparent height profile, which is proportional to the charge density. So this is a bright spot is a higher charge density, and the dark is lower charge density. So when you're using tight band calculation, you can get in the wave function. So the square of a wave function actually presented in the charge density wave. Yeah. So we can compare it. It's sit on two-dimensional, but there is a wire, so quasi one-dimensional structure. Yeah, along the yes, upper, lower. This is upper chain profile, and this is lower chain profile. This is upper, lower, upper, lower, upper, lower, upper, lower. When you say upper, lower, means this chain stacked along the G direction? Oh no! Actually, you are looking from the top, but we put in the wall, so it's a upside. This is up and this is down. So it's just for convenience, not the up and down. So chain one, chain two, more appropriate notations. Because we have two zigzag chain, so each zigzag chain can act as a simple 1D chain. So it's yeah. Actually, this is a lot of to talk about in the this is a chiral soliton, but it's today's object is not. So I want to skip briefly. So we also checked their density of state using the scanning tunneling spectroscopy. Then we compare with tight band calculation, the match well. So then actually that is what I want to talk about here. What is we call the chiral soliton? Because their wave functions then representing belong to the certain atomic site. Then is they have certain pseudo-spin vector. The pseudo-spin vector actually rotating along the chain. Each chiral cases, or chiral cases, they only change in the amplitude, not the change. So in that sense, actually, this chiral meaning can have a meaningful because it is they have vector, right? So vector, so we can rotate two different direction or not rotating. and the Akara cases. So that's why we started to look at the now and the ground state, not the soliton. Soliton itself is a chiral, but it's ground state, and nobody talk about this chirality. So that's why. So this is a large-scale STM imaging. Then we identified each ground state as a color. So as you can see here, their fracture exactly similar one-to-one. So which is they are really degenerate. But when you look carefully, we can define that there has certain order. For example, in this area, I starting from the bottom, so it's the okay. First, I mentioned in the now I'll switch in the notation, ground state notation. This is A, B, C, D. Okay, more simpler way. So in here, in this area, starting from D, C, B, A, which is opposite order in the alphabet, and the other area start to A, B, C, D, and also different area AD, AD, the other way BC, BC. There has certain order. So I wonder what makes this certain order. This may be related in the color order in the whole system or just as a coincidence. So before going on, we analyze first in their symmetry. So in the pristine and metallic phase at the higher temperature, they have a mirror symmetry. As you can see, this is a mirror plane. So when you apply the mirror reflection, we see this exactly same structure, right? But when you cool down, the form in the CW, then is this mirror symmetry becomes broken. Okay, but this broken symmetry now can act as a connecting operator between the two different ground states. Over here is a M1 mirror plane. Actually, it's not mirror symmetry plane, but when you apply it in the mirror reflection in these structures with respect to M1, then becomes in the B structures. And also, we use M2 mirror plane, then we becomes in the D structures, which is each broken symmetry actually can act as a connecting operator between in the ground state. So we summarize like here. So A is we can transform into B through the M1 mirror plane, but also D becomes realized through the M2. And also we use a half translation along the chain, which is this A and C as the same shape, but is different position. So we can move with half translation, then becomes C. So A is connected in the half translations. So then we formed this is symmetry operators maps. So using that, actually, if you stack to another wire, so we call it like a AD structures, then it's using in the M1 middle plane, A becomes B, so A becomes B, and the D becomes C, which means these two structures energetically identical because we can use the symmetric operations, right? That means they are energy the same. So when you're using the DFT calculation, we only calculate this one. Then we know this one's energy. Another case is this AD now is transformed to the DA through the M2, right? M2, AD, DA as switches. So this A becomes D, D becomes A. And also, if you use translate, then is A becomes C, and the D becomes B, D becomes B. So it's AD, CB is identical structures actually. And Then we can draw this conclusion. This AD, BC, CB, DA is identical form, basically. Another possible form is in the BC. Actually, AB, BA, CD, DC can be actually can be switchable each other. So okay. So, based on this symmetry analysis, actually we only need this distinct structure to get as idea their energy difference. So this is AA, which means the same structures each other. The other one is AB, AC, and AD. Actually, this AA, AC actually not were not found in the real system because it's not allowed, as you can see in the later. But anyway, when you look carefully in the AB and AD, they have a certain symmetry, which is glide symmetry. So this is a dashed line, the vertical dashed line is a glide plane. So when you apply this glide plane, the first mirror reflection, so it's A becomes B, B becomes A. Then half translation along this plane. Then it's come back to its original form. Same thing in the here, but with a different glide plane. So then we did in the intensive tight binding calculation to see which is the lowest ground state. Then each is a band structure over here. And we noticed is this F and H actually is identical to in the RPS measurement. But in the EG is totally different because of the gamma point, this conduction band much lower than in the X point. Here is a different, right? This is quite a distinct difference. So we confirmed the energetics later. So this one almost degenerate. And also we found is MY direction, so the band is degenerate, which means that they has a certain symmetry to protect this degeneracy, which is a glide symmetry over here and over here. So they have a degenerate over here. But is in the AAAC, it doesn't have a degenerate over here because they don't have this kind of a glide symmetry. All right, here energetics is each combination they give is a different energy, but we found the lowest energy configuration is AD. So with respect to AD, we can give is a relative energy difference. So the next lowest energy is AB over here. AB is this is very close the energy. So it's almost degeneracy, but slightly different. This is lowest, but second lowest, but this energy difference is not that big. Actually, this structure looks similar, but previous in the DFT calculation, actually they don't distinguish. They randomly choose one of them. So, but this first time we actually distinguish these two structures and find in the true lowest structures. Then the main thing is what about we expand the wire stacking? So we actually we have two choices, right? Start from A, B or D, right? But we know that in the AD is a slightly lower energy. So I put this solid line for that, and the higher energy is I'm using in the dashed line. Okay, then now is B. Then we have a choice A or C. Same thing, A. We have a choice like it. In this way, we can stack it. Then we found the lowest cases only 3 choices, which is we repeat the 2 of them, AD, AD, like here. The other one is start from A, B, C, D, come back A, B, C, D. Like the other one is AD, CB, A. which is opposite the order. So as you can see here, we can actually define another vector, which is when you look at the a hexagon, actually a hexagon move in the next neighboring wire in the right direction slightly. They come back to left, right, left. Then when you consider the entire unit cell, there is a effective moving. Actually, there is no effective moving. So they don't have a chiral over here. But here, they keep moving left direction. The other one keep moving right direction, which is they becomes chiral order. They we call the chiral order. And also, this chiral order can realize in the order parameter space. So AD-AD, they are keep back and forth AD-AD, which means they don't wrap around in the point 0. But here, ABCD, they wrap around entirely in the 0 point, right? Yep.
What was the reason you cannot go from A to C?
Because of high energy. Yeah, AC is the highest energy. Yeah. Energetics. Actually, the experiment is also we confirmed a long time ago. They shape is always alternative return, which means they don't like a chiral pattern. Actually, A and C actually a chiral pattern. They just translate, right? So they are not chiral pattern. So they preferred chiral pattern only. Yeah. So actually, this is actually, we can repeat many, many wire, like a 6, we can have actually a 32 possible cases. But when you carefully, this 32, like 6 wire, actually we can cut in the 4 plus 2, right? So 4, we are already discussed over here. 2 is, we have 2 choices. So many wire, we can also repeat that this is subdivided into the 2 choices, 4 and 2 choices. But in the other number of cases, it's not allowed because the other number always neighboring wire becomes a chiral pattern, which is not energetically allowed. So this is other number we are not allowed. Only is even number wire, but even number wire we can consider 2 part, 4 or 2 cases. Okay, then this is energetics. Okay, if there is isolated wire, you can do, but this is self-assembly process, so they have many wires at the same time. Yeah. Okay, that's a good point. Yeah. Yeah. Mm. Yeah. ABA itself is no problem, but this is unicell. You have to repeat. So ABA, then AA is come together. Yeah, that's why I crossed out. Yeah. So this is we got from in the density functional theory calculation. So we found AD again is lowest energy. So with respect to that, we have give a relative energy difference. So AB is the highest energy difference. So experimentally, we cannot find these structures, but we easily found is ABCD, ABCD, and the ADCD, which is a chiral form. This is a chiral form is the lowest one, but it's a chiral form is very close to each other. But when you look at here, energy difference less than milli-electron volt in the whole unit cell, which is extremely small difference. So in the DFT guide said this is just arbitrary number, so we cannot say it's any energy difference between two them. Yeah. So and also experimentally we can find in this structure actually intertwined each other. So it's red is right chiral form is over here, and the blue in the left chiral form. And the dashed line in the here uncolorized region, actually in the achiral region. So they are as a coexist, intertwined each other. But I empathize in actually this structure looks same, but energy difference to this is not allowed in the real system. Yeah.
Why do you have energy difference between the middle two choice?
Middle two choice actually
They are chiral partner.
it's chiral partner, but it's this silicon substrate. We didn't consider silicon substrate so far,
It's only
but
because of
yeah.
the substrate.
Yeah, substrate to play some role. So there has significant role.
So that's not
Yeah.
intrinsic property.
Yeah.
If you just consider these two patterns, they should be
Yeah.
chiral partner.
Yeah, should be chiral pattern. Yeah. And now we are talk about in the defect. So we often see there's some structural defect. As you can see here, this is defect actually in the indium atom on top of in the CW wire. So this indium defect actually translate in the one wire in the half unit cells by half unit cell. So it's A becomes C. But when you look at around this defect, so start from A, B, C, D. So this A, B, C, D winding in the counterclockwise. Same thing happened over here. Different situation, but it's this winding is the same. But the other defect, like this single defect, this is a double defect, come together, then is a B translate D, right? But start from A, B, C, D, this direction. So this winding is now becomes clockwise, which is this. The defect also gives some chirality. So we this kind of structure people called is a chiral vortex. And also, we often see that in the, this is, look at here, this is the ABCD. This is also ABCD, which is this chiral order, this chiral order exactly same. But they has a actually meet at a certain boundary. We call it is this is chiral domain wall. But this chiral domain wall actually exists only same chirality. Different chirality, actually, we cannot see this kind of form in the specific dissolved system. So let me summarize my talk, almost hour. So we found in the chiral ground state in the quasi one-dimensional child density wave, and also this chiral ground state can be stacked in the in the two-dimensional surface. A different chiral still can coexist, but this is chiral actually prepared because due to energetics. This is lowest one is a chiral form, and almost degenerate the other chiral form is also possible. So here we define in the phase shift vector. So this phase shift vector actually give as a chirality. We can distinguish between the two, three orders. As confirmed, this chiral order can coexist in the surface. Okay, thank you for your kind attention and nice introduction. Yeah.